This video is going to look at the theory behind volumetric analysis. Volumetric analysis, also known as a titration, is an analytical method used to determine the exact concentration of a substance. It's a very widely used technique used to determine the exact concentration of pharmaceutical drugs. It's used to determine the fat content or the salt content in lots of food. It's used to look at the acidity of wine, and also used to look at trace elements present in water. In a titration, you have two solutions. One of them you know the exact concentration of. This is called the titrant. The other one is the one you're trying to figure out the concentration of, and that's called the analyte. Since you know the exact concentration and volume of one solution, you can use this equation here to figure out the moles of the known solution. Then, once you've balanced your equation and you've got your reaction stoichiometry, you can use the mole ratio, in this case 1 to 2, to figure out the moles of your unknown solution. Then finally, you can use this equation and the moles of your unknown solution to calculate the concentration, as you know the volume of your unknown solution as well. This is what the titration may look like as you're doing it. So you may have your known solution in the burette, so it's got its exact concentration, and it's also got the average titer volume here. Now note, this is the average of your concordant titers, usually within plus or minus 0.1 of a mil, not all of your titers including your rough titer. In your conical flask, you might have your unknown solution, so we don't know the concentration yet, but we do know the volume. And note how this is a very precise figure, including 4 significant figures, because it will be delivered via a volumetric pipette. The solution with the known concentration is referred to as the standard solution, and it's prepared using a solid called a primary standard. Now, when we choose a primary standard, we have to take several things into consideration. The first one is that it should react in some sort of detectable way with the analyte. So if you're trying to determine the concentration of an acid, you should really choose a base as a primary standard because it can undergo an acid-base reaction. The next thing is that it should be available in a reasonably pure form. This is because when you weigh it out, you don't want any of that mass to be impurities. You want it to be all of the primary standard. Now, if you look on the bottle or the container and it says analytical reagent, that means that it's one of the purest forms available. It should be stable both in air and water, so you can store it without it decomposing, and once you dissolve it in water, it's not going to break down. One of the things that we quite often rule out solids as being used as primary standards for is because they're hygroscopic. As you can see here, this is sodium hydroxide, and it's been absorbing moisture from the air, again meaning that when you weigh it, part of that mass will be water, not just the solid. It needs to have a large molar mass. This is because you want to weigh out a high mass, not a low mass, because that will be more accurate on the scales if the scales have a resolution of, say, plus or minus 0.01 or 2 grams. And the last thing that we look for is that it has to be soluble in water, because most of our titrations are carried out under aqueous conditions. A titration is stopped at the end point, which is when the first faint permanent colour change is observed. So this picture up here would be a good end point because it's a very faint colour. This one down here is not, because the colour is far too intense, so the end point has been overshot. Now, if you're doing an acid-base titration, you need to add an indicator to determine where your end point is. Ideally, there should be a really sharp or distinct colour change at the end point. So a good example of this would be phenolphthalein, which goes from colourless below about pH 8.5 to bright pink above pH 8.5. Ideally, you also want it to have a colour change around about pH 7, because at the end of your acid-base titration, all of the acid will be neutralised by the base. If you're carrying out a redox titration, there are several options. Potassium permanganate is actually self-indicating, so this can be the reactant but also the coloured indicator. Potassium permanganate is like bright pink or purple in colour. When it's reduced, it gets reduced to the manganese ion, which is colourless. The other one that you can use is the starch indicator, and that's used to indicate the presence of either iodine or iodide, and it goes from this very deep blue-black colour, again, to colourless. The end point of a titration is where you get your first faint permanent colour change. This is not the same as the equivalence point, which is when the reactants are present in their stoichiometric ratio. So if you look at the balanced equation, it's when you've got exactly that ratio of reactants present in your conical flask. Now, this might help explain that a little bit better. This is an acid-base titration. You're starting off with an acid and you're adding in a base as your pH rises. So here your equivalence point will be at pH 7 when all of the acid has been neutralized by the base and no excess base has been added. However, you might be using an indicator that has a colour change around about pH 9. Now, as you can see here, there's a really small difference in the volume between the amount of base that's been added at the equivalence point at pH 7 to the end point at pH 9, because we've got this very steep section of the curve here. So although it's not ideal, we use the end point as the best possible estimation of the equivalence point. Aside from a standard titration, there are two other types of titrations that we have to learn. The first is an indirect titration. This is used for a substance that might be volatile or insoluble. What happens here is in the first stage of the reaction, we react what we want to find out, so our analyte, with something else that's in excess, and we produce a product, which is D. Now this step here is not the titration, it could just be done in a beaker. Then we take D, the product, and we undergo a titration with D, which now becomes our analyte, with E, which is our titrant, so our known concentration and volume. So from this titration, we can determine the number of moles of the concentration of D, and we can work backwards to find the concentration or the number of moles of A. Now, an example of this would be determining the exact concentration of ammonia in an air sample. So ammonia is a gas, so we can't undergo a titration with a gas. So what we do is we react with that ammonia with an excess volume of water. That's really important so that we make sure that the ammonia is the limiting reagent. And we produce ammonium hydroxide. So again, this first step is not the titration. Now, we take the ammonium hydroxide, the product from the first reaction, and we undergo a titration, in this case with an acid, because ammonium hydroxide is a base. And when we get to our end point or our equivalence point, we can work out the number of moles of ammonium hydroxide, the unknown solution or the analyte, and therefore we can work back to figure out the number of moles or the concentration of ammonia. The other sort of titration that we have to know is called a back titration. And again, this can be used for a reactant that is volatile or insoluble. So here we react A with B, and we need excess B. We take any B that is left over, so that hasn't reacted with A, and we use that for our titration in our second step. Again, this first step here is not a titration, it can be done just in a beaker. It's the second step here that is the titration that allows us to work back and calculate the number of moles of A. Now, an example of this could be that you've been given a sample of limestone and you want to determine how much of that limestone is calcium carbonate. So calcium carbonate's a solid, so obviously you can't take this and titrate it. So you react it with an excess amount of hydrochloric acid. You have to know the volume and the concentration here. The next stage, you take the leftover hydrochloric acid, so all of the calcium carbonate would have been used up, but not all of the hydrochloric acid would have been used up. So you take the leftover hydrochloric acid and you take this in a titration. So react it against the base, so you can figure out the number of moles or concentration of your hydrochloric acid and work backwards to figure out the number of moles of your calcium carbonate. This might help explain it a little bit better. If you know the exact amount of hydrochloric acid that you add in, so the total amount, you can calculate the amount that you've used in the titration, and so this remaining amount over here will tell you how much has reacted with the calcium carbonate, and therefore how much calcium carbonate is present.